Okay, here's our last video of section 5.1. We're going to do example number 4. I want you to remember though, when we talked about section 4.9, we started talking about antiderivatives and integration. Do you remember the problem where we took the velocity and we integrated it? We found the antiderivative. And we said that the antiderivative or the integral of velocity, remember, was the position function. Well, that's kind of what we're going to do here, but we're not going to have a function anymore. We're not going to have an actual equation to find the antiderivative of. So what we can do is we can use our Riemann sums, our rectangles, and we can estimate the area underneath the curve, which is the same as the antiderivative. So let's look at example number 4. Example number 4 says, suppose the odometer on our car is broken and we want to estimate the distance driven over the 30-second time interval. Hey, be quiet. Wait, please. Sorry. So we want to estimate the distance driven over the 30-second time interval. We take speedometer readings every 5 seconds and record them in the following table. And so at 0 seconds, we're traveling at 17 miles per hour. At 5 seconds, we're traveling at 21 miles per hour, and so on. So we have times and we have velocities. But it's not asking me for velocity, it's asking me for really a distance traveled, a position, right? And so how can we go from velocity backwards to position? Well, we know that we can take the antiderivative, or the integral of. The problem is we don't have an equation to antidifferentiate or integrate. But we talked about in the last few examples that using area underneath the curve is similar to estimating the antiderivative value. And so what they did on this one, to make sure that the units kind of match, instead of seconds here and hours, they converted it into feet per second in the second table. So let's use the second table instead, with time in seconds and velocity in feet per second. And let's figure out the distance that I traveled over those first 30 seconds. And so I imagined this graph, and I knew that I was going from 0 to 30. And when I'm looking at these numbers, I was 25, it went up 31, 35, 43, 47. It looks like it increases and maybe decreases a little bit. So I kind of sketched that graph. I knew it was going to kind of increase and then maybe decrease a little bit. And remember, this is the graph of the velocity, okay? I want to use it to estimate the area underneath the curve, which should be the same as my antiderivative or my position or distance traveled. Let's go ahead and take this interval from 0 to 30, that's 30 units total, and let's divide it into rectangles that are 5 units wide, because that's the information that I have in my table. I'm going to go ahead and do right endpoints, and I'm going to do left endpoints. I'm going to do both. If I was doing right endpoints, I'm going to take each of these from the right of my rectangle, follow it up and over, follow it up and over, follow it up and over, and so on. If my function is increasing and I'm using right endpoints, is this going to be an overestimate or an underestimate? It looks like it's going to be an overestimate this time, right? So let's look. I know that each of my little rectangles are going to be 5 wide, so the widths of my rectangles are 5. Let's figure out what the heights of my rectangles are. So if you look at the first rectangle, the height, the y value, corresponds when x is 5. The next one corresponds when x is 10, 15, 20, 25, and 30. So I'm going to use those values, plug those into my function so that I can find the height of each of my rectangles. So f of 5, using my table of values, I get 31. F of 10 is 35. I get 43, 47, 45, and 41. That's the base times the height of those different rectangles. I can add them all together, and I can approximate that the area is 1,210. So now if you look, do you remember all of these values here, the 31, the 35, the 43? Weren't those velocities? Those were feet per second. And so when I added them all together, I got 242 feet per second. But do you remember the 5 here? Didn't the 5 correspond to the widths of my different rectangles, or my x value, which was really seconds? And so if I take seconds and multiply it by feet per second, then didn't we just actually find feet? Which should make sense, because if this graph is really the velocity graph and we're finding the antiderivative, shouldn't that be the distance or position, which the unit should then be in feet? And so I can estimate the distance that I traveled from 0 to 30 seconds as 1,210 feet by just knowing the velocity. Okay, let's do it again for left endpoints. So if I'm looking at left endpoints here, I need to change my graph a little bit. Maybe let's use black here. I know that each of my rectangles is still going to be 5y, but I need to use left endpoints now. So if I go from the left over, from the left over, from the left over, then I know that all my rectangles are going to be below, and so my estimate is going to be an underestimate. If my function is increasing and I'm using left endpoints, I know that I'm going to have an underestimate. Let's find the height of all of these rectangles. If I'm using left endpoints, I know that the first rectangle, the height corresponds when x is 0. The second rectangle, the height, the y value, is when x is 5. The next one, x is 10, 15, 20, 25. Let's see here, would be my last one, right? Don't go too far over because we're using left endpoints. Using my table of values, plugging in all of those numbers. 226, remember, is a whole bunch of different velocities. This is feet per second. The 5 is really 5 seconds, and so I end up getting a total of 1,130 feet. The 1,200 was an overestimate. The 1,100 is an underestimate, so the distance traveled is somewhere in between 1,200 and 1,100 feet. Okay? So again, the area underneath the curve is really helping me find the antiderivative from A to B. If I know a velocity, then I can figure out the position from 0 to 30 seconds, antiderivative. And so what if I asked you to do lots of different rectangles? Well, we can estimate the area underneath, and the more rectangles we have, the better the estimate gets, right? And what's the best amount of rectangles? Well, isn't it infinite? And so in the next section, we're going to talk about what happens if I ask you to find the area of an infinite number of rectangles.